equal to 0, nothing will come in EPR. Here you can go for NMR, but that won't provide you any information related to EPR. So it has to be S equal to not equal to 0. Okay. Now, how to get EPR active compound starting from a closed cell situation? Now, as far as the radical is concerned, so that is rather simple to understand. For example, if you go for homolytic cleavage over here, then you will be getting radical, right? So this RR bond cleavage would gives you R radical and R dot radical. If RR, then you cannot distinguish. If R and R prime, then you can get the two different radicals over here. So here, the radicals recombination, if it takes place, you will be getting a bond. And if it breaks, through the homolytic fission fashion, then you will be getting radical. On the other hand, in a metal complex system, you can get it through oxidation or through reduction. You may have a compound, say if I consider iron 2,1 compound, octahedral, tetrahedral, whatever, octahedral you consider it, and if it is a low spin iron 2, that means it will be T2G6, all the 6 electrons would be paired into the T2G level. So it will be a closed cell situation. But if you oxidized it to iron 3, then it will be T2G5. Then you will have one unpaired electron. On the other hand, if you reduce it, then you will be getting iron 1. That is a D7 system. That means one unpaired electron would be in the EG level. So you will have eventually you can generate that unpaired spin containing molecule from a closed cell molecule via oxidation reduction for metal complexes, or for organic molecules you have to have the radical generation, and then you can do it. But the problem of the organic radicals, most of the organic radicals are very reactive and short-lived. Okay, and you will see those who are very much interested in organic chemistry, you will see that either you will have nucleophilic pathway or the radical pathway in the reactions, either catalytic or non-catalytic. Now, how to differentiate it? That whether it is passing through a radical pathway or a non-radical pathway. So EPR is one of, NMR cannot help you to understand that. So reaction mechanism, if you need to understand, and where your intermediates are very short-lived, okay, it cannot be trapped by any other technique other than your EPR technique, because you can do the same reaction within the EPR cavity. So the radical it generates, and even if it's generated and it's very short-lived, you can freeze it immediately, and you can record the spectrum at a very high scan rate over there, and you will get a lot of information, particularly whether the reaction is following the radical pathway or the non-radical pathway. On the other hand, metal, here probably the cationic and anionic species, the radical species, radical means radical unpaired electron is located on the metal center, may not be as reactive as that thing. So one can trace it at low temperature with the proper experimental setup is necessary. Okay. Now, what information we could get out of EPR? Now, there are two ways to understand it. One, from the physics point of view. If you go from physics angle, then a lot of wave functions, etc., all sort of things you can get out of these experimental techniques. But as a chemist, we only try to understand that what is the electronic feature of that paramagnetic molecules. Now you could feel in the beginning, oh, it's so simple. There is one unpaired electron, there will be certain responses, one could feel it, and that's all. But the issues are not that simple. There are many contradicting complications and complicated issues are there. And that is how we need to understand the electronic structural aspects would follow in a particular molecule. And moreover, very interestingly, that it's very difficult to derive a general feature over there. That means with one molecule, you have struggled a lot, you got the spectrum, you analyzed the spectrum, you did calculations, and so many things, whatever you prefer to do and whatever accessible to it, and you got certain parallel informations. Now you could feel, well, I got this feature, so now for my PhD or for my life, I will prepare 100 molecules, and this idea could be extended to the rest of the molecule. No, it is not so. That's the problem with the EPR. That means you cannot derive a general statement, moving from one molecule to another molecule. Every molecule behaves differently due to a variety of factors. You will understand it later, and then you need to check it other way. Now, disadvantage, that is the advantage part I said from physics and from chemistry point of view, but it has serious limitations. The limitations are you have to have one unpaired electron, either half integer or integer. Here I have just written integer, but it could be integral value also. You have to have at least one unpaired electron, if not more, unlike NMR. And its resolution is not as good as NMR, but the other thing is that that NMR you can do it at room temperature. And mostly we do the NMR at room temperature, and we get very good NMR. Organic molecules, so fantastic NMR. Even for complex metal complexes, we can get fairly good NMR spectra at room temperature. But that indeed, does not happen in case of EPR. You have to go to very low temperature, not only low temperature. In many occasions, even liquid nitrogen temperature, that is 77 K, which is not enough to get the reasonable to necessary resolution of the spectrum to understand it. You have to go down to the maximum possible low temperature, say 4K, by using liquid helium to get a fairly resolved spectrum. So all sort of issues are there. Those are considered to be the disadvantage as far as the EPR is concerned as compared to your NMR is concerned. Now, as I said, that for a molecule to be EPR active, you need to have at least one unpaired electron, if not more. Now, the nature, if you see our nature, there are certain paramagnetic molecules, not many, but there are certain paramagnetic molecules. I have just drawn two. These are our biologically relevant, very important molecule. Say molecular oxygen, and if you put the unpaired total electrons, 4 plus 4, in the simple MO diagram, there are two possibilities that these two electrons could be paired up in the antibonding orbitals, and then you will be getting singlet oxygen. But under normal circumstances, we don't get the singlet oxygen, we get the triplet oxygen, because singlet pairing of these two unpaired electrons in the antibonding orbital requires is an energetically uphill process. So that's not the normal circumstances. So it's a triplet molecule. Okay, and its EPR spectrum would be completely different than